This is the video for analyzing the effect of a on a quadratic function. By the end of this lesson, you will be able to describe how the value of the leading coefficient affects the graph of a quadratic function, which is what we mean by the letter A. You will use your calculator and a table of values to make conclusions about different A values. So at the top of your worksheet today, it says to complete the tables for each function. So there are 3 of them here: y equals x squared, y equals 2x squared, and y equals 1/2 x squared. So you'll complete the tables, then graph and label each function on the coordinate plane. So at this time, I'm going to ask you to pause the video so that way you can use your calculator, get your table of values for this one. Same thing, and get the table of values for this one, and plot your points and create your quadratics. So please practice this at this time and pause the video. Okay, I hope you have your tables and graph filled out. Here we go. Let's see what you should have on your paper. So here are your table of values. Notice each of these we're just going from a domain of -3 to +3. And here are your values, so double check them. And let's check out what your graph should look like. At this time, you should have 3 quadratics or 3 parabolas on your graph, all of them labeled as well. Okay, so your graph should look something like this. You'll notice that not only did I plot the points that were in the table, but I also plotted any point that fits on this graph. We always want to plot as much as we can. Okay, so you'll notice with each of these functions, remember that this one, x squared, is really the parent quadratic function. And for each of these, the only value that we have changed is the leading coefficient, the value of a. So here, a is equal to 1. The next one, a is 2. And the last one, where a is 1/2. So today is all about checking out what this does to the graph and how it changes the parent function. So letter A says to describe the effect of the leading coefficient on the y values. So we're not talking about the graph just yet, we just want to focus on our y values. So let's say here that when a is 2, how did the y values, these guys, how did they change from the parent? So from 9 to 18, 4 to 8, 1 to 2. I'm hoping that you've noticed that the y values doubled. So we'll just write that they doubled here. Okay, why did they double? Because now we're doing everything from the parent but multiplying it by 2. So our outputs have doubled. When a is 1/2 in the third table, do you see what happened to the y values here? We went from 9 in the parent to 4.5, from 4 to 2, from 1 to 0.5, 0 to 0, and so on. So here the y values are halved. Okay, now let's analyze the graph a bit. Letter B. How does the graph of y equals 2x squared, so we're looking at the one here, the one in red, change from the graph of the parent, y equals x squared? So how does the one in red change from the one in blue? I'm hoping that you notice that y equals 2x squared makes the parent Can you think of a word that describes the change from the blue one to the red one? If you're thinking of the word it got narrower, you are correct. So it makes the parent function narrower, or more narrow. So this happens because a is 1 in the parent, and now it's 2. So it has a greater rate of change. You may think of this as slope, but remember, quadratic necessarily doesn't have a constant rate of change or a specific slope, so the rate of change is getting higher which is why our graph gets more narrow, or the slope gets steeper, if you want to think of it that way. Letter C. How does the graph of 1/2 x squared change the graph of the parent? Well, this one up here was in green, and the parent was in blue. So we can say y equals 1/2 x squared makes the parent. If we use the word narrower up here, then down below we can use the word wider. Okay? Or we can see that our a value, which affects our rate of change, the rate of change got smaller or decreased. Smaller rate of change, which means our slope, if you want to think of it that way, isn't as steep as the parent. So we can see here that changing the a value in these two changes the way the parent looks. Notice the vertex for all of these stays the same. It's just a matter of getting narrower or wider. Letter D says to calculate the rate of change for each of these functions over the interval where x goes from 0 to 3. Do you remember what the word rate of change really stands for? If you're thinking of the word slope, you are correct. So this really stood for slope to help us out. And they want us to do it over the domain where x is 0 to where x is 3. So I'm going to make a table here for y equals x squared, a little section. Y equals 2x squared. And over here, y equals 1/2 x squared. Okay, so if I need to find the rate of change for each of these, then I need to find the slope. Do you remember the slope formula? It is y2 minus y1 over x2 minus x1. Okay, so for y equals x squared, from 0 to 3 means that we will use when x is 0 to when x is 3 as our two ordered pairs. So this is x1, y1, x2, y2. If I plug in those values into the slope formula, we would have 9 minus 0 over 3 minus 0, which equals 9 over 3, which is equivalent to 3. So the rate of change for the parent is 3 when x is 0 to when x is 3. Let's check out the same thing for when y equals 2x squared, when x is 0 and when x is 3. So x1, y1, x2, y2. Let's plug them in to our formula. And we will have here 18 minus 0 over 0 minus 0. Oh, I'm sorry. 18 minus 0 over 3 minus 0, which equals 18 over 3, which is equivalent to 6. Okay, so we can see that the red one here has a greater rate of change than the blue one. This one is 6, while this one is 3, which makes sense because this one, the leading coefficient is 2, while the parent, the leading coefficient is 1. Let's do the same thing for the last one here. Let's take a peek when x is 0 to when x is 3. So we will plug in these values and find the rate of change. So we will have here 4.5 minus 0 over 3 minus 0, which is equal to 4.5 over 3, which equals 1.5. So which one of these has the greater rate of change? We can see here that it's the y equals 2x squared, and when I look back at my graph, we can see it has the greatest rate of change because it's the steepest, or it's the most narrow. So this one here is the narrowest because it has the greatest rate of change, whereas the one with the smallest rate of change, or the slope, would be the widest one. It's not as steep, and we can see that in our graphs. The green one here is definitely the widest. So we are going to sum all of this up on the next side, as well as using our previous knowledge of what we know about a quadratic in vertex form. Okay, we've talked about these letters in the past where we have seen what A can do to the graph, what H can do, and what K can do. So, do you recall what H comma K represents? Okay, remember that this is really the vertex. So we can gather a bunch of information from this vertex form. Now we're going to talk about the sign of A. Okay, by the sign of A, we mean positive or negative. So remember, the sign tells us which way it opens. When A is positive, we will get a parabola that opens upwards. You can just draw in a little sketch. And when A is negative in the front, the leading coefficient, we know it'll open downwards. Remember that another way to say that it opens downwards is that it gets reflected over the x-axis. But our focus for this lesson is more so going to be on the value of A, meaning what the actual number of A is. So we saw in our example on the front that the value of A is really going to tell us how wide or narrow the parabola will be. We can also summarize that when A is greater than 1, the graph gets, well, let's look back at the front. When A was greater than 1, this one's 1, this one's 2, so this one, did the graph from the parent, the one in blue, did it get wider or narrower? And it did in fact get narrower. Okay, remember that happens because the rate of change is increasing, so it's really getting steeper. We'll use the word narrow. Or, sometimes you might see the phrase, it vertically stretches. It's a vertical stretch. It's reaching up higher than the parent. When A is less than 1, which it also has to be greater than 0, the graph, let's see what happened before. Here we had when A was between 0 and 1, it was a half. From the parent to the green one, it ended up getting wider. Remember, that's because the rate of change is smaller, so it's not as steep as the one before it. So this one is wider, and we're going to call that vertical compression. We'll talk more about these two phrases in class tomorrow. Okay, so it's up to you to be able to spot when a parabola will get wider or narrower, or to be able to pick out the one that is the most narrow and the one that is the most wide. So let's put this into practice with one last example here. The following functions are shown on the graph below. Identify each of the functions shown by writing the function name in the box that corresponds with its graph. Now, we can definitely use our calculator to help us see which one is the most wide or the most narrow. But let's use our understanding of the number that A is in each of these. For example, we can see here that A equals negative 1, A equals negative 2, and A equals negative 3. So remember, from our notes, the sign tells us which way it'll open, which is why all of these parabolas here are opening downwards, because the sign is negative. But now we're going to take a closer look at the value, the 1, the 2, and the 3. So, let's start where A is negative 3. This one has the greatest rate of change. So if this number, or this value, is the highest, do you know which graph h of x is modeling? The highest rate of change, or the steepest one? If you are thinking about this purple one, you are correct. So in this box here, we will put h of x. Try to squeeze it in there. Okay. Now, which one do you think will be the most wide? The widest one. Remember from our notes, that is the one with the smallest A value. We're ignoring the negative, we're just looking at the 1, the 2, and the 3. And in this case, it is f of x. x. This one has the least rate of change, which means it'll be the least steep, or it'll be the widest one. Therefore, f of x, do you see which one it is? Is the blue one. So put an F there, which means the 2, which is in the middle of the 1 and the 3, we can automatically assume is the green one, g of x. Okay, so tomorrow we are going to practice identifying graphs, whether they will be the most narrow ones or the most wide one, and all of the different possible effects that A has on our graphs. Please write down any questions or comments that you have to begin class tomorrow. Thank you.